Yeah, welcome back after the short break. What we are discussing is common base amplifier, and we will be going for common gate amplifier. But before going to that, I do have another example based on the common base, where we are talking about practical circuit of this base bias. Instead of having ideal separate voltage source here along with the Thevenin equivalent resistance R B, practical circuit wise we may have only one supply voltage, and from that we need to generate whatever the voltage we like to generate here. So, we can have a potential divider constructed by say R A and R B connected to ground, which generates the voltage here. And also we may have a situation that instead of having this ideal current source, we may have some practical component, either active device or passive bias circuit. So, in our next example, what we will be concentrating on, it is common base amplifier, but then with more practical bias arrangement. So, in the next slide, that is what we do have the example. Here, as I said, that the voltage for the base, we are generating this base voltage by VDD, and then the potential divider constructed by R A and R B. And the value of R A and R B are given here. The other information about the BJT as well as the other parameters are remaining same, which are enlisted here. The RC, intentionally we are making slightly different value, or I should say we have made some change here, and at the emitter, instead of having ideal bias, we do have R E, and its value it is given here close to 10 K. In fact, we are considering 10.3 kilo ohms, so that with a beta of 100, we can get the emitter current or rather collector current very close to 0.5 milliampere. So, and also we are considering the signal source resistance of 10 K. So, the effect of this resistance we already have discussed. In this numerical example, primarily what we are focusing on, as I said, that we do have practical bias circuit, and in case if we have practical bias circuit, using that, how do I find the operating point of the transistor? So, let us try to see the operating point of the transistor by considering R A, R B and so and so. Now, in this case VDD also I have changed. So, instead of 10 volt it is 12 volt, and R A and R B both are 100 K. So, we can say the voltage source coming to the base, it is actually it is 6 volt. So, this 6 volt it is, we can say it is Thevenin equivalent voltage in series with Thevenin equivalent resistance, which is R A in parallel with R B, incidentally that is 50 kilo ohm, and then it is going to the base of the BJT, and then at the emitter DC wise we do have R E here, and it is 10.306 kilo ohm, and the current flow. So, we are expecting that there will be a current flow, and let me call this current is I B, and if the transistor here it is in active region of operation, this I B current it produces a current here which is 1 plus beta times I B, right. Now, base to emitter node we do have VB on of 0.6 volt. So, if I redraw this circuit considering base 2 emitter voltage, then what we have, it is 6 volt Thevenin equivalent voltage source, 50 kilo ohm resistance coming from R A and R B in parallel, and then we do have a drop of 0.6 base 2 emitter voltage, and then we do have a this current flowing through R E, which is 10.306 kilo ohm, and the current flow here, it is I B, whereas this current flow, since we do have the collector current which is beta times I B. So, we can say this current is 1 plus beta times I B. So, if I consider this loop, and if I see the potential drop, so 6 minus 0.6 equals to I B into 50 K plus 101 plus beta is 101 I B into 10.306 K. So, that gives us I B equals to, here we do have 5.4 divided by this 50 K plus 101 and multiplied by this one. I think I do have some calculation on that. So, roughly you can say that this is 1041 K, and that gives us close to 4.95 microampere of base current. Now, if I multiply this base current with beta, I can get the collector current, and the emitter current is of course 1 plus beta into this I B. So, that gives us very close to 0.5 milliampere. In fact, for simplicity, collector current also we can consider this is same as the emitter current, and that is 5 no 0.5 milliampere. So, we got 0.5 milliampere current flowing here. So, the drop across this R C, it is 6 kilo ohm and 0.5. So, that gives us voltage drop across this R C, V R C, it is 3 volt, and then the collector voltage, it is 12 minus 3 volt. So, that is we do have 9 volt, and the voltage coming at the base, of course, there will be base current flowing here. So, it is not just entire 6 volt, it is coming here. In fact, I should consider this drop also, and this current, it is, as you have seen, it is very small, close to 5 microampere. So, 5 microampere multiplied by 50 kilo. So, that gives us this drop equals to, so the drop across this resistance, it is 50 K multiplied by 5 close to 4.95, we can say approximately 5 microampere 10 to the power minus 6. So, that gives us minus 3 here, and yeah. So, this is 250 into 10 to the power minus 3, or we can say that this voltage it is 0.25 volt. So, the voltage coming here it is 6 volt minus 0.25. So, the voltage DC voltage coming here it is 5.75. That ensures that device it is in active region of operation, and of course, the voltage coming here it is 5.75 minus 0.6. So, that is 5.15. That is how we can get the operating point of the transistor. Now, once you obtain the operating point of the transistor, then again we can go for calculating the value of the small signal parameters, namely Gm, R naught and so and so. So, let me clear this board and then let me write those things. So, small signal parameters Gm equals to IC divided by Vt. So, this is 0.5 divided by 26. So, I should say this is 1 by 52 mho, and then RO it is VA early voltage divided by IC. So, this is 50 volt divided by 0.5 milliampere. So, that gives us 100 K, and R pi it is beta, which is 100 divided by Gm. So, that is 52. So, that is 5.2 kilo ohms. Now, once we have obtained the small signal parameters, then rest of the things it is you yourself can do, namely you can calculate what will be the input impedance and so and so. So, those things I will not be going to I will not be repeating. Now, next thing it is that it is also important to see the output swing in this, particularly in this practical circuit. Yeah. So, the next thing we are going to talk about the output swing of the circuit, and as we have discussed that the supply voltage it is 12 volt, and RA and RB both are equal to 100 K. So, that gives us the Thevenin equivalent voltage here at the base node it is 6 volt, and the Thevenin equivalent resistance it is 50 K. Now, if I consider the base terminal current of 5 microampere as we have discussed before. So, if I consider the IR drop with respect to Thevenin equivalent voltage, so at the base terminal the DC voltage it is coming 5.75 volt. On the other hand, the collector current here it is 0.5 milliampere. So, the drop across this RC, and RC value it is 6K. So, the drop across this 6K it is 3 volt. So, that gives us the DC voltage at the output node, which is equal to 12 minus 3 volt. So, that is 9 volt. So, we do have the DC voltage here it is 9 volt, and at the base we do have 5.75. So, while we do have the signal riding at the collector terminal, so with respect to 9 volt, the instantaneous collector voltage it can go as low as 5.75 before this base collector junction it is getting forward bias. That means the device coming out of the saturation region. In fact, you can have this junction weakly forward biased by an amount of roughly 0.3.
So we can say that the collector voltage, it can go even lower than 5.75 by an amount of 0.3. So the amount of signal swing we can tolerate here is so 9 volt is the DC minus 5.75 minus little forward bias we can tolerate, it is 0.3. So that gives us 9 minus 5.45, so that is equal to 3.55 volt. So this is what the output signal swing in the negative side. So this is the possible output swing in the negative side till the transistor it is entering into saturation region. On the other hand, if I consider the positive swing, now we consider output swing in the positive direction. So with respect to 9 volt here, the voltage here it can go as high as 12 volt. Even though we know that there will be significant amount of distortion because of the exponential IV characteristic of the BJT, but let you consider that is the limiting situation. So the corresponding positive swing, it is equal to 12 volt minus 9 volt. So that is equal to 3 volt. Of course, once you consider the input signal, it is sinusoidal. So we have to consider minimum of these two to finally conclude that what is the signal swing of say sinusoidal signal it can tolerate. Now coming to the other aspect, that the input impedance of this circuit, it is expected to be low. So if the source resistance it is significant, so then the input signal, it will be experiencing significant amount of attenuation. In fact, in practical purposes, when say RS if you consider in the range of kilo ohms or say 10 kilo ohms, it will be having significant, I mean quite I should say large amount of attenuation. So instead of considering the circuit in the form of feeding the signal in the form of voltage, in practical purposes we consider let the signal be fed into the input terminal in the form of current. So in other words, typically the common base amplifier we want to consider as current amplifier. So the next item we need to discuss it is the what may be the current gain of this amplifier.
First of all, the stimulus part here we need to replace by say current source, signal current source. Maybe we can consider this is I in, and it may be having a finite conductance, and this is conductance is 1 by R s. Now this signal it is going here, and again through this capacitor the signal it is arriving to the emitter node. Now once we have this I in, we are feeding at the emitter node, and then we like to see how much the current we will be getting here, particularly in unloaded condition. And for unloaded condition, what we mean is that we have to basically short it. We have to short it to the AC ground, and while we do have this I in current, what is the corresponding produced output short circuit current. So for this current gain, you may recall that the current gain it is very close to 1. In fact, we do have the if I say that we are sorting this node here, that means the corresponding VO equals to in fact this is 0. And if you recall the model here, small signal model here, we do have this RO, we do have the GM here multiplied by VBE, and VBE it is minus VE, and its minus sign can be taken out. So, the small signal model of this circuit, it can be written like this, and then the output node it is shorted, and we are observing the corresponding output current there. At this node we do have the signal here I in, assuming that this part it is 0 conductance. So, we can say that I in it is entirely flowing through this, producing a voltage of VE here, and then we do have the RE part. Also we do have the R pi part, and R pi, other terminal of the R pi, it is connected to ground. So, the current flowing through this RE and R pi, it can be directly obtained by considering this VE by RE or VE by R pi and so and so. So, I am just writing whatever we have done in the previous day's derivation, that I in is VE divided by RE, VE divided by R pi, and then this divided by R naught, and also multiplied by GM. So, on the other hand, I O it is VE divided by R O and GM. So, from that we obtain the current gain A I equals to I O divided by I in. If I consider these two equations, what you are getting here, it is 1. So, GM plus 1 by R O divided by, in the denominator, GM plus 1 by R O plus 1 by R pi, and then 1 by R E. So, why am I writing here? Now, we can compare each of these terms, and you may recall the value of the GM. GM it is 1 by 52 mho, and the R pi it is 5.2 K, and RE it is 10 K. So, 10 K, and then we do have R naught, which is 100 K. So, by considering all these practical values of different parameters, naturally you may say that this GM it will be dominating over 1 by R naught. In the denominator also this GM it will be dominating. So, we can directly say that this current gain it is very close to 1. If you want to get better approximation, probably you can retain this part, and then you can find what will be the value here, and instead of 1, to be more precise, it will be then beta divided by 1 plus beta. In fact, this is alpha, which means that if we have this I in, it is entering here at the emitter, the corresponding available current at the collector, it will be alpha times of this transistor. So, obviously, this alpha it is very close to 1 depending on the value of the beta, though mathematically it is less than 1, but as I said it is very close to 1. So, that completes the analysis of the common base amplifier. Now, similar kind of analysis can be done for common gate amplifier. In the next slide, we will be discussing that. But I must say that for common gate circuit, we can consider ideal bias, and we already have done this exercise for common base. So, instead of going with the ideal bias and then going for the practical circuit, I prefer directly go into a numerical example where we will be having this kind of biasing arrangement. So, in the next slide we do have the common gate amplifier having the practical bias arrangement. Now, obviously, the finding the operating point of the MOS transistor, it is slightly different from BJT, and that may be one important exercise we must try to do with this. Now, we do have the different components values are given here, namely R A and R B, same as the previous case. So, we can say at the gate node we do have 6 volt getting generated by this R A and R B from this 12 volt supply, VDD supply. So, we do have 6 volt here, and then that is coming in series with the Thevenin equivalent resistance of R A in parallel with R B, which is 50 K. And then we do have the MOS transistor, and then we do have the R E. I should not say R E, I should say rather different resistance, and it is its value it is 4 kilo ohm. Now, how do I find the value of this IDS from this circuit? What we can do, it is we can make use of the parameter of the device, assuming the transistor it is in saturation region. So, if I say that IDS current is flowing and that is creating a drop here, at the gate of course, the current is 0. So, we can say that the 6 volt it is directly coming here. So, VG it is 6 volt, and source voltage it is such that VGS it is supporting the required current here, which is exactly producing this IR drop. So, we can say that the 6 volt minus this 4 K into IDS, that produces the VGS. So, if I say that IDS equals to K W by L by 2 into VGS, and VGS is 6 volt minus VTH of 1 volt minus this IR drop, which is 4 K into IDS, and its square. So, here we do have IDS equals to 1. So, this part it is 2 milliampere divided by 2. So, that is 10 to the power minus 3 into this is 5 volt, 5 minus 4 K into IDS square. Now, we do have this second order equation, and if you solve this second order equation, what you will be getting here it is IDS will be having two values. One of them it is the actual one, other one it is hypothetical one. and the correct one you will be getting, it is 1 milliampere. In fact, you can cross check it. I have done this derivation, but yourself can cross check it. And how do you do this one? How do you obtain this one? I am just giving a tips. So, we do have this part, it is 4k multiplied by IDS. So, we can say this parameter, if I multiply here, what I will be getting here, it is 4k, 4 into 10 to the power 3 into IDS equals to 4 into 10 to the power 3 into 10 to the power minus 3 into 5 minus 4 into 10 to the power 3 into IDS square. So, that gives us say this part, and we like to calculate this IDS, and let you consider this is equal to x. So, this is also x. So, that gives us an equation x equals to 4. So, this part and this part is getting cancelled, we have 4 here multiplied by 5 minus x square. So, what we are getting here, it is 4 x square minus 10 and 4, basically 40 x plus 25 into 4, 100. So, that is equal to x. So, from that you can get an equation which is 4 x square minus 41 x plus 100 equals to 0. So, from that you can get the value of x, and once you get this x, you can find the corresponding value of IDS, and one of them it is this IDS. In fact, you will be getting another IDS solution here, which is impractical, namely that will make this source voltage, it is higher than the required voltage here, pushing this transistor into cutoff. So, that solution you can ignore, and you can retain this 1 milliampere of current. You can, in fact, you can verify this one. Say if we have 1 milliampere of current flowing here, the drop here it is 4 volt. So, if I am having 1 milliampere of current, the voltage coming at the source, it is 4. Here at the gate we do have 6 volt. So, the VGS it is 2 volt. So, VGS minus VTH is 1 volt. So, that gives, say this part, this entire part it is 1, and this part it is 1 milli. So, that gives us IDS is equal to 1 milliampere. So, anyway, so that is how you can get the IDS, and then the drop across this R1 it is 3 kilo ohm multiplied by 1 milliampere. So, that gives 3 volt here, ensuring that this transistor it is in saturation region of operation, and hence the circuit is in good condition to amplify the signal. So, end of it what you obtain here, it is IDS equals to 5 milliampere, sorry 1 milliampere, and different VDS and the VGS we obtain. So, we obtain the operating point using that. Let us calculate the small signal parameter. So, let me clear the board and then again calculate. So, IDS as I said equals to 1 milliampere, and hence GM of the transistor, which is having an expression of 2 IDS into k W by L. and this is 2 into 10 to the power minus 3 into kW by L is 2 milliampere per volt square. Sorry, this should be volt square. So, this is 2 into 10 to the power minus 3 ampere per volt square. We do have ampere here. So, that gives us Gm equals to 2 milliampere per volt. The other parameter we are looking for, it is RDS, small signal parameter RDS, and this RDS, it is 1 by lambda into IDS, and lambda, it is given here, it is 0.01 per volt. So, this is 0.01 multiplied by this is 1 milliampere. So, you can see 10 to the power minus 3. So, that gives us RDS is equal to 100 kilo ohms. So, we obtain now the small signal parameters, and then we can proceed for the voltage gain. So, what was the expression of the voltage gain we have for this circuit? AV, let me use different color here. So, the voltage gain AV equals to Gm into R1 in parallel with RDS, and Gm, it is 2 milliampere per volt, and R1, it is 3 K in parallel with 100 K. So, again you may approximate or probably you can calculate more precisely. I think I do have that calculation. This is to be more precise. This gives us this is 2 milli per volt multiplied by 2.9, yeah, 2.9 1 kilo ohm. So, that gives us overall gain, it is 284. You can no 5. Yeah. So, you can see that the gain here, it is very small compared to the common emitter amplifier. That is expected mainly because value of the Gm for MOS transistor, it is quite low. So, even though this R1 and RDS in parallel, it is having significant amount of resistance, but because of smaller value of this Gm, the voltage gain, it is quite low. So, even without considering this RS, we do have this problem. Now, if I consider this RS, so this gain of course, it is from source node to drain node. Now, if I want to know what will be the voltage gain from the primary input to the primary output, after considering this RS is equal to 10 K, then we need to calculate what will be the corresponding input impedance. So, the input impedance of this circuit, of course, it is you may see that it is getting dominated by 1 by Gm. Let me use different color to derive that or calculate that. So, R in, so the R in, it is you can well approximate by 1 by Gm in parallel with R2, right, and this Gm we already have obtained here. So, that is 1 by Gm, it is 0.5 K in parallel with R2, it is 4 K, and yeah. So, that gives us 0.444 kilo ohm. So, the input resistance here of this circuit, it is not as low as common base circuit, where GM it was much higher, but still this resistance it is much lower. And if I consider source resistance of say 10 kilo ohm, that further degrades the signal from primary input to the source node. So, the overall gain, if I say overall gain, I need to get the overall gain A V overall. So, let me use different color. Yeah. So, A V overall. So, that is A V multiplied by this attenuation offered by R in and this R s is 10 k. So, that is R s plus R in. And this attenuation it is we can, let me use this space here. A V we already obtained, it is 5.82, and then this attenuation it is 0.444 divided by 10.444. So, I do have the corresponding calculation of this gain, and it becomes 0.24. So, what you can see here, it is the gain it is much lower than 1. So, this is primarily because for this case this circuit itself it is having low gain from here to here. In addition to that, the input resistance is low, and we are considering a practical source resistance that further attenuates the signal before going to the source node. So, I should say that the voltage gain it is low. The input resistance we already have calculated. Output impedance it can be calculated in the similar way we already have done. Input capacitance of this circuit, it is similar to the common base, namely input capacitance it is CGS, and from that we can say that we can calculate the input the upper cutoff frequency defined by R s and input capacitance. So, those things I will not be repeating that, but I must say about this output swing. What we said here, it is the gate voltage it is 6 volt, and the voltage at the drain it is 12 minus this 3 volt drop here. So, that is 9 volt here. So, if the DC voltage at the drain node it is 9 volt, VTH it is 1 volt. So, this voltage it can go as low as 6 minus 1. So, that means it can go to 5 volt, as low as 5 volt. So, with respect to 0.9 voltage DC, the corresponding swing towards the negative side it is 9 minus 5 volt, that is the 4 volt. So, we can say that the negative swing it is 4 volt. Sorry, the slide is becoming very clumsy. Let me clear it and then again rewrite this part. So, what we said here, it is 9 volt DC, voltage here it is 6 volt. So, at the output node we do have the 9 volt here and the voltage here it is 6 volt. So, we can have the signal swing like this. If this is 6 volt, it can go as low as up to 5 volt, because threshold voltage is 1 volt. So, the swing here, signal swing we can get here, it is 9 volt minus 5 volt. So, that is the 4 volt negative side. On the other hand, positive side it can go as high as 12 volt theoretically, but of course, the corresponding signal may get distorted like this. So, the corresponding swing on the positive side, however, it is 3 volt. So, anyway, for this design, that is what the operating point and that is the corresponding signal swing. This information it will be useful whenever we are going to design a circuit. So, that we will be discussing later. Now, next item it is the current gain of this circuit. Current gain for this circuit it will be it is you may recall on the previous discussion, this current gain it is very close to this GM, or rather let me write that expression, GM plus 1 by RO divided by GM plus 1 by RO plus 1 by R2, and R2 it is we already have discussed, it is 4K, and this is definitely it is quite small compared to GM. So, again here we can approximate this by this GM it is getting dominated. So, we can say that the corresponding current gain it is approximately 1. In fact, if you see, if you ignore this resistance, whatever the current it is entering, signal current is entering to the source, the same current is flowing here approximately. So, that is an indication that the circuit current gain it is common gate amplifiers current gain it is close to 1. So, that completes the numerical examples whatever thing we have planned. Based on this information you can probably, okay, I do have one more numerical example. Probably I will cover this one in the next class, because if I start explaining it may be it will take more time. So, let me break here, and then of course, after this one we will be having a plan to cover design guidelines. So, what we have to cover here, this numerical example, and in this numerical example it is yeah. So, in this numerical example what is the important point here, it is in case if we are not using the CB, what kind of effect it may come, and this is important for common base amplifier. So, this numerical example it will take some time. So, let me come back on this example after break.